For today's quiz, we've got an inductor, and this is a large inductor. Inductor is really a coil that can build up magnetic fields. This one's special. I've got lamination here that can slide into the coil or out. I have an AC supply here connected in line with a light bulb that goes through the coil and back to our neutral. Our question is this: if I have the bulb illuminated, which I can show you, it will illuminate. Plug this in. We've got our bulb and it's lit up. Our question is, what's going to happen whenever I pull the rest of this laminate core inside the coil? This is what your quiz looks like. As always, mark your answer as completely as possible. Enlist your confidence. Typical student responses that we get are, A, when I pull this coil in, the light is not going to change at all. This is just a piece of wire. It's really long, but I use the same amount of wire. Yes, it's in a coil, but it's still the same length of wire. It has the same exact resistance. Good thinking. The others will say that no, this is going to act like an electromagnet. And when I put metal in an electromagnet, it seems to help that electromagnet pick things up. So when the core is pulled in, it'll get more magnetism of some kind. And so therefore they think the bulb is going to get brighter. Others will just guess and say, I really don't know. So those are our major thoughts. All right, so let's actually do the experiment. Then we can talk about it afterwards. When I pull the laminate core in, watch our light bulb as I pull it in, you can see it dims and eventually goes out. I put it back out, it comes back on. This is really interesting stuff. I want to show you something. I'm going to put an ammeter on here, so give me a second. All right, I've got my AC ammeter on, and you could see the light bulb here, and this is an incandescent, so it uses a lot of power. And I'm on my 10 amp scale because I'm above 200 milliamps, and that's just in between my selectors on this meter. But you can see whenever I pull this in, it goes from 0.2 or 0.3, and it goes all the way down and nearly approaches zero. But why? Why is this happening? Well, remember, this is AC. And we're going to end up having a changing magnetic field because of the changing current inside the coil. But when we have these laminate strips, and I want to point out that this is a really good coil. Now, whenever we're talking about inductance, that is the susceptibility to doing something with those field lines, this is going to be made out of iron, which has nearly a multiplying factor. You can think of it like that as being like 200, but it can go all the way up to like 20,000 if you increase the amount of nickel in here. And so what's happening when I pull this in, the frequency of this, which is set at the power company, is going to end up trying to make magnetic fields grow one way and then the other. Now, you might think of this as inertia, and this is going to be a little bit strange, but I have another device that can show us how this might be similar to inertia. Let me set that up. At this point, students are pretty comfortable dealing with mass. Mass has this property called inertia. That is a resistance to change in motion. And that's going to be helpful for understanding this inductance. If I were to put this mass onto this spring device, and these are just thin, straight springs, it'll bounce back and forth. As this thing is accelerating one way, the springs here are going to try to pull it back the other way. But it doesn't happen instantaneously. It's going to take a little bit of time, and that's what's really going to set our frequency. So if I used more mass, it's going to be harder for that restorative force to bring it back. So it's going to end up slowing things down. So as I increase the mass, it's harder to get this thing to switch back and forth. When we're talking about our inductor, it's similar. Oh, I don't know if you can hear this, but it's vibrating now. Let me see if I can get this to stop. This is a good one, and I'll talk about this in a minute. But anyhow, what is different about this mass inertia is that the frequency can change. When we're talking about our electrical system, our frequency is set at the power company. So as this is trying to build up a particular amount of magnetic field, it's going to need to do that every 60th of a second. So it's going to need to collapse and build the other way and so on. When I end up putting my laminate in here, it's going to make that effect even greater. So if I just had something more like an air coil, the field lines can probably keep up. But not when I put these laminate pieces in here. Now it's going to try its best to make the field lines, but it's going to make so many of these field lines, it just can't do it and keep up at that rate. And therefore, it literally gets like clogged up or choked off. So this is going to end up impeding our current through here because it can't keep up with the rate demanded by the change in its frequency. So you might think, well, this is a lot like a dimmer switch. And it is. You could use this as a dimmer for your lights at your house. Normally, we're going to end up using big coils where we'll end up taking a lead and striking one of those as we move it up and down for a variable resistor. But you could just as easily use a big coil like this to dim your lights. Now, there are places where we use this. We don't actually use these for dimmer switches very often. You could, but this thing is 25 pounds, very expensive as compared to other types of methods using resistance. And again, this is not using resistance. But I have one last thing that I want to show you where we use this all the time. All right, I'm down in the shop, and I wanted to show you a massive coil. You might be asking, where's the coil? Well, it's behind this sheet metal. Inside this AC welder, also known as a buzz box. We'll get to the buzzing in a moment. There's a massive coil, and we can vary our AC amperage output from 35 to 230 amps. The way that we're going to vary that is just like what we showed earlier. We have a massive coil, and we have laminated strips that we're going to take in and out of the air coil itself. That is what this lever is going to do, and it's going to vary our overall current that flows, just like our light bulb turning on or off, except this time we're going to be melting metal. It's nearly impossible to be down here without getting dirty, so I'm going to get changed, and then we'll see if we can get a better look inside of this. I put the welder on its side. The vents are large enough to see the internals. I'll point a few things out. First of all, it's unplugged. There is no capacitor inside. There's nothing to worry about in terms of an electrocution hazard. Down here, this little white blade, that's just a fan to cool this when you're welding. I've got a massive iron core that goes around, and it's essentially an air coil or air core at this point. Here is my laminate sheets going vertically. On each side, I have a little bit of Teflon. That'll allow it to slide in and out. This is essentially a transformer. It's two coils. I've got my primary and secondary. It's a step down. As I end up putting the lamination into the core, I can change the amount of output that I'm going to get from this welder. Right now, I would have the maximum amount at 230 amps, but if I slide it in, hopefully you can see, I'm going to slide that in, and now I'm going to choke off most of the current. And in this case, we're rated at, it looks like 45 amps. So it's a simple, cheap, easy way of regulating your AC current, especially for a welder that doesn't have to be a precision device. All right, I've got my air vent on, and I've got the buzz box hooked up, and it's ready to go. I'm going to weld just a piece of scrap here and let you know why we call it a buzz box. I'll stand in front because I don't want to overload the camera in terms of the UV coming off. So let me just give you an idea what this is like. You could probably hear the buzzing. That's why we call it a buzz box. And the reason why it's buzzing is as we're changing those magnetic fields, you could see that laminate coil was not fitting in perfect. It vibrates in there. If you make it too tight, it wouldn't vibrate, but you'd also get it stuck. So that's how these AC welders work. And that is your quiz for today.